Welcome to a beautiful morning near the Salton Sea, specifically the southern edge of the Salton Sea. We're looking at the rising sun, one of the geothermal power plants there. And if we wheel around here to the north, we see the Salton Sea itself. And today we're looking at Obsidian Butte, one of the Salton Buttes, one of the volcanoes. It sits at the southern edge of the Salton Sea. Thanks for joining me. I'm Geology Professor Shawn Willsey, here to provide you with some little excursion, a little field trip, if you will, looking at different parts of this region of the West. So let's start with why we have volcanoes at the southern edge of the Salton Sea. Obsidian Butte is one of the Salton Buttes. I think it's about 5 volcanoes collectively that are more or less aligned along the southern edge of the Salton Sea. But let's look at a regional map to explain why we have volcanoes here at the Salton Sea area. So here's my fun little map I put together. Spent a lot of time on this. So here we have the US-Mexico border, California, Arizona. The green are the mountains. So that's the peninsular range that runs up and down Baja California and then comes up east of San Diego and Los Angeles. And then of course we have the notorious San Andreas Fault, which begins on the eastern edge of the Salton Sea and then proceeds another 1,200 miles to where it terminates off the coast of Northern California near Cape Mendocino. We're right here. I only drew 3 little triangles. There's actually 5, but these are the Salton Buttes right here along the southern edge of the Salton Sea. And I've got other faults drawn as well. So we have the San Andreas Fault, then there's the Imperial Fault, which extends over the border into Mexico. Another fault, the Cerro Prieto Fault, which heads down into the Gulf of California. And then from that point, we have a series of strike-slip faults. That's shown by these big black lines here. But those strike-slip faults are connected by a series of divergent plate boundaries as we go into the Gulf of California. So the Gulf of California is both a divergent plate boundary where the plates are spreading, but also a strike-slip plate boundary. So it's what we call sometimes an oblique divergent plate boundary. It's accommodating both extension in more or less a northwest southeast direction, but also there are strike-slip faults that allow one side to move towards the other. Remember, the whole thing is driven mainly by the Pacific plate, which is moving more or less in this direction shown by my pen here. So why do we have these volcanoes here? Well, we can see what's happening in the Gulf of California. These strike-slip faults are really just connector pieces. They connect adjoining divergent plate boundaries. So if you have one divergent plate boundary here and another here, the way to connect those, given the plate motions and the sense of movement on those divergent plate boundaries, is to have a strike-slip fault, in this case a right lateral strike-slip fault. As you stand on one side and look across, the movement is to the right. So we can see those very nicely with bathymetry looking underneath the water in the Gulf of California. But when we come onto land here in this portion of the Southwest, things get a little bit tricky, because we have the Colorado River, which forms the California-Arizona border, and then it dumps into the Gulf of California. And the Colorado River has dumped so much sediment in this region that it largely obscures seeing the faults well, at least at the surface. So we have the Cerro Prieto Fault here, but then there's an offset where it steps over to the Imperial Fault. And right where this step over occurs, there's a volcano, the Cerro Prieto volcano. And we have a similar situation here with the Imperial Fault and it terminating here, the San Andreas Fault here, and then the Salton Buttes forming right here. So it's really a divergent plate boundary. The Salton Buttes is sitting over a developing divergent plate boundary. The only reason we don't have the ocean in here, because we are below sea level at this location, is because the Colorado River has dumped so much sediment into its delta region that it's built up enough sediment to keep the ocean at bay. But undoubtedly at some point in the future, as this spreading continues, the Gulf of California will extend up into the Imperial Valley, reoccupy the Salton Sea region as it did formerly when it was Lake Cahuilla. And then it will also go up into the Coachella Valley up here with where Palm Springs is. Let me show you one other diagram that will hopefully explain some of the other features we see in this area, because what we have in this region is pretty remarkable. We have the Salton Sea, which sits below sea level, and then just over the hill here, I'll walk up there in a few minutes, there's large mountains. There's mountains above Palm Springs that rise over 11,000 feet. So the question might be is, how do you get such crazy topography? How can you have land below sea level right next to essentially land that rises almost 2 miles above sea level? How do you get such a contrast between large towering mountains and very low land? And the secret to that, the answer to that question, lies in how the plate, let's start with this one, how the plate motion and how the plate boundary go together. So if the plate motion is in this cartoon here off to the northwest, and this is absolute plate motion, so this plate here is pulling in that direction, but plate boundaries are not always parallel to plate motion. So if the plate boundary is perfectly parallel as it is here, then you get a perfectly strike slip fault. But sometimes plate boundaries take advantage of pre-existing weaknesses, could be thermal anomalies in the rocks that cause the plate boundary, the line between the two plates, to be a little bit different. So let's assume in this case that the plate boundary actually goes something like this. So it makes this kind of like a soft Z shape, I suppose. So here the plate boundary is parallel, so we get strike slip motion. Up here, the plate boundary is parallel to the plate motion, so we get strike slip motion. But in here, where it runs at a counter to it in terms of a different angle, notice that we would have something different. If plate motion is absolute, then this part of the plate is moving away from this other plate here. So we would end up with a divergent, a little zone of divergent plate activity. We would end up with extension, and because we have extension and we're thinning the crust, that causes the crust to subside. This is also where you would see magma rising as the pressure is reduced from the overlying crust, and we would end up with volcanoes forming here. This is exactly the situation we see here at Obsidian Butte and in the Salton Buttes. And this is what's known as a releasing bend. So when you have in this case, a rightward bend, if you're looking in the direction of plate motion, if it bends to the right, then you end up with a little bit of a zone of divergence or stretching, which causes the land to sink. This is why the Salton Sea area sits so low and actually is below sea level. If we look at the contrasting situation, so again, we'll assume same plate motion off to the northwest like this, but now what we're going to do, let me grab a rock here, but now what we're going to have is a different bend in the plate boundary. So now the plate boundary comes and takes a leftward bend. So down here where the plate boundary is parallel, again, strike slip motion, sideways horizontal motion. Up here, same thing. But here where we have this bend, remember that this arrow is the one that we're beholden to. So this would cause compression. This part of the plate would actually be compressed or converging with this other plate over here. So we would end up with a zone of compression. As we take two pieces of the crust and compress them together, we would end up thickening the crust and creating mountains. And this is one of the reasons you see more or less east-west trending mountains in Southern California, like the San Gabriels, the San Bernardinos. Some of those other mountain ranges are running east-west or east-west-ish because of these small little bends. And I drew this bend as being quite pronounced, but now just imagine it a little bit more subtle and you'd still end up with the same type of geometry. So pretty cool. I think that's a neat part of the story here, with the interesting topography we see down in this region. So let's look around at Obsidian Butte a little bit. The sun's just coming up, so the lighting's just perfect. And what right away we can see in looking at the rocks, that these rocks are very well layered. You can see the layering in the rocks in front of me here going more or less vertically up and down. And Obsidian Butte's not all obsidian. We can see a nice little patch of it right in here where it's really shiny. But like other videos I've done, obsidian, we know, comes from silica-rich or felsic magma. And so you'd expect there to be pumice in zones where the magma or lava had a lot of gas to it. If there was a little bit of crystallization, we would call that rhyolite. So it's a combination of both rhyolite, obsidian, and pumice. And this specific volcano here, Obsidian Butte, erupted about 2,000 years ago. So it's pretty young. This is actually one of the most volcanically active areas in California. If you were to take, or if you were to place a honest person's wager on which volcano in California would erupt next, this would be as good a chance as any, even more so maybe than Mount Shasta or some other volcano, Long Valley Caldera, or some other place you might be thinking of. So the Salton Butte erupted mainly this silica-rich felsic magma. And you might ask, well, wait a minute, if this is a divergent plate boundary, why would we get felsic magma? Because if you remember, when you create these divergent plate boundaries under the ocean, the type of magma that erupts is basaltic magma, mafic magma, silica pore magma. And there's a couple different ideas here. No one's exactly sure, but one idea is you've got the Colorado River off to the east that has dumped literally tens of thousands of feet, literally miles of sediment into this basin, into the Salton Trough. So as that mafic magma comes up and encounters that thick pile of sediment, most of which is very quartz rich, that it changes the chemistry of the magma a little bit, and you end up with felsic magma at the surface. That's one possibility in one model. It could be crystal fractionation, could be other processes, but mainly we're erupting felsic magma here at Obsidian Butte. That magma would be sticky and pasty when it erupts as lava, so it's just oozing out of the ground like toothpaste. And that's really what you see when you see these flow lines here, this pattern of layering that we see in the rocks, is because this stuff's just oozing out of the ground, and it's so stiff and sticky that it doesn't flow away like most lava flows you're familiar with. So this is a lava dome. I believe all the other Salton Buttes are one form or another of lava domes. This particular one, Obsidian Butte, started out explosive, and when we get down to the shore here in a bit, I'll show you some of the pumice from this. But there is pumice here in place, but there's some nice particles down there of pumice as well. So it started out explosive, eventually just oozed out this sticky, pasty lava that didn't flow very far, just sort of piled up on itself. Again, you can see that real just the viscosity of the material by looking at some of these outcrops here where it's just sort of sticking up. In places you'll see it's kind of folded, might be just a little bit of folding. Other places it might be more folded upon itself. And they've quarried some of the hills, so you can see up here some of this rock's been moved and quarried, but everything we're looking at here is still in place. Here's some of the more porous material here that looks a lot more like pumice. You can see some of the holes in that material. Some of the pieces are pretty light to pick up. So again, that pumice obsidian, it's sort of a continuum depending on the gas content in any given particle. So let's head down. This is near the summit of Obsidian Butte, just to give you a look at this. What we'll do next is head down along the shore, or close to the shore of the Salton Sea, where there's a little bit better pieces of obsidian to look at, because I know a lot of folks really like obsidian. Here's a nice little zone in here of some obsidian with some crystals in it as well. Not nappable obsidian, but this obsidian here at Obsidian Butte was used by native people for tool making, so it was a prized resource and a known locality among indigenous people. So let's head down here to the edge of the Salton Sea and take a look at the rocks down there. Okay, I've come just a bit to the north of Obsidian Butte. We're looking south, so you can see the profile of this lava dome. Fairly low relief. You can also see, and maybe even hear, the geothermal plant working there in the background. There's another one over here. And so they're tapping that shallow heat that exists just not very far down in the subsurface. So they're tapping that and generating that into electricity. So we're down here where there's some outcrops of obsidian, because I know a lot of folks love obsidian. So nice shiny face here. You can see the swirling pattern as this viscous lava just sort of rolls over onto itself. Some of the small little white specks here, these are called spherulites, so that's where it's starting to crystallize. So a little bit more pure obsidian down low in this outcrop, and then mixing with some of the gray rhyolite as we go up. Let's head down though off this berm. I know there's some more pieces of it down here, and take a look at some of these other outcrops down here. We'll wrap up down here. So as you get down to the beach, where, you know, the Salton Sea rises and falls with climate and inflow. Gosh, if I gave the Salton Sea its proper credit right now, there'd be another 30-minute lecture, and maybe I'll do that at some point. But basically, it's been much higher than it is now. And so what we're standing on here is areas where it was once much higher, and you can see the wave energy here has tumbled a lot of these pieces of obsidian into little polished, rounded rocks. The other thing you'll find over here that I mentioned previously are pieces of the pumice. So these more beige colored rocks are pieces of the pumice that were erupted when the initial phase of Obsidian Butte produced explosive conditions. This frothy pumice was ejected, and then this stuff probably, as the lake's risen and fallen, these actually float out on the water, and so then they get rafted up onto a shoreline. The waves kind of pound them, and they end up becoming pretty rounded. You can see these frothy, with the gas bubbles in them, these pieces of pumice. So nice little contrast here, the dark obsidian. Here's a bunch of the pumice over in here, and with some other stuff. So let's head around this corner here and see. I think there was a really cool exposure of obsidian. And then a lot of the white you're seeing here, I don't know much about the biology here, but it's a big shorebird environment. So a lot of this is shell material or skeletal material from some of the fish that live in here. So you can see some of these little bones, but this is all organic material, all this white material here. I'm sure someone will educate us all on exactly what's going on there. Here's a really sweet exposure of the obsidian right here with some of the great banding, the flow foliation on it here. That's just a really nice exposure. Yeah, stuff's hard, glassy, and then you can see it grades down into a less glassy material. But all these little black rounded rocks, if you break them open, they are pure obsidian. So they end up weathering, and so they don't look quite as shiny on the surface, but then you break them open and you can see that typical glassy look that you know and recognize as being obsidian. So there's some fun little boulders down here, some other big outcrops down there. So we'll go ahead and wrap this up, but thanks for joining me on this lovely morning, kind of a cold morning, wearing a jacket at the Salton Sea. Doesn't happen that often, but in December, that's what you get. So hopefully you enjoyed this look at Obsidian Butte, looking at the Salton Buttes, how they formed, their origin, how the plate boundary and the plate motion work together to produce this zone of volcanoes here at the south end of the Salton Sea. That allows the geothermal activity to occur, which fuels these power plants. Also, largely responsible for the incredible topography we see down here as well. So thanks again for joining me. Stay well, and be sure to like, share, subscribe. There's a thanks button at the bottom of the viewer. There's donate buttons under the description to the video as well, if you'd like to donate to me producing and making these geology videos. But till next time, we'll see you at the next stop as we take one last look at the beautiful Salton Sea.